Okay, so we get a polynomial. The question is how good of an approximation it is. So this theorem on polynomial approximation, you can read in black and white what it says. Let me explain to you what it means. That this f being an element of the continuous functions or functions with n+1 continuous derivatives on a, b. So basically it's a function that's just as good as you need it to be. And here we have p is our polynomial of degree at most n. Okay, that's going to interpolate this polynomial f at n+1 distinct points. Okay. So for every x in this interval AB, there is a c sub x element of AB such that f of x minus p of x is equal to 1 over n+1 factorial times f n+1 evaluated at ski sub x times this product pi I equals 0 to n of x minus x sub I. Okay, so this over here is the error. Okay, this is how far it is wrong. The 1 over, okay, this 1 over n+1 factorial, that will make the error small. This, it's just sort of a wash. It's not going to be too bad. This here, unless our roots unless all of our knots here are close together, this has the potential for being pretty big and to giving us some big errors on our interpolating polynomial. Okay, so I want to prove this, and so this is a proof that it's had somebody's done quite a bit of work on it, trying to make it look easy. The price of that is you might not necessarily know where it's coming from, but okay. We define this function w of t to be a product of the differences between t and all of our interpolation points. Okay, I'm going to define then a function phi of t to be, okay, f of t minus p of t. So this is the difference between our our function and the interpolating polynomial at the point t. This right here is just some constant, with a parameter x in it, and then this wt is that function up there. Okay, and if you take this, function phi and substitute in x for the t, everything falls out, and your function is equal to 0. It's equal to 0 at that point. Now, since this factor in square brackets depends only on x, and we're a function of t, I'm just going to put a lambda in there for it and pretend that it's constant, so that I can write this all in much shorter form as phi is equal to f minus p minus lambda times w. And the f and the p and the w are functions of t, and the lambda is a constant with respect to that. So note that we can check that phi is 0 on every one of our knots, okay, and that phi of x is also equal to 0, and so that means that phi itself has n+2 zeros. So by Rolle's theorem, okay, we can check that phi prime has to have n plus 1 zeros. Why? Because it has a zero, the derivative is a zero between the zeros of the function, okay? Phi 2 has n zeros, for phi double prime has n zeros for the same reason. It has a zero between each zero of the original function, and we can keep on doing this until we get down to phi n plus 1 only has 1 0. Okay. Now, let's choose this c sub x so that phi, the n plus first derivative of phi evaluated at the c sub x is equal to 0. So that's the magic number, okay? So go back and, we have this expression for phi here. Take the derivative of it n plus 1 times, and you get that the n plus first derivative of phi is the n plus first derivative of f minus the n plus first derivative of p minus lambda times the n plus first derivative of w. Okay. Now, but p is a polynomial of degree n, so if you take its derivative n plus 1 times, it's just gone. Okay, so we've simplified this expression to be this one. Now, what about that w? Recall your w comes from here. It's not all that complicated a polynomial. It's a polynomial with n t's in it. If you carry that out, you see your w of t is going to be t to the nth plus a bunch of polynomial terms, but none of the t terms has a degree bigger than n minus 1. You take its derivative, and all your powers of t go down. They might get messy out here on this right-hand part, but don't worry about it, because we're just going to keep taking derivatives until we get down to those all being 0 and only having n plus 1 factorial left over. So the n plus first derivative of w evaluated at t is n plus 1 factorial. So roll that back in to this guy right here. And you get this guy right here, okay? Now, put in that magic value of ski that makes that equal to 0, and so by 0 is then equal to this, and I can now solve for that lambda, and the lambda, okay, is equal to f of the n plus first derivative evaluated at c sub x divided by n plus 1 factorial, and we're done. It's over. Right? This is what we wanted to prove. Okay. Now, let's look at an example here. Let's suppose that p interpolates sine on the interval from 0 to 1 at 10 points. So f of x is equal to sine of x. If you take its derivative once, that's cosine. If you take its derivative once, it's negative sine. You start toggling through that. If you do this 10 times, the derivative is, and I lose track, it's either sine or negative sine. Let's pretend it's a sine. And so the absolute value of the 10th derivative of f is at most 1, because it's sine. And so all of my roots are in the interval from 0 to 1, so no pair of them are going to be farther apart than 1. So if you take their product, that's less than 1. And so here we can see that sine of x minus p of x is going to be less than or equal to 1 over 10 factorial, which works out to 2.76 times 10 to the negative 7th. And if we graph it, we can see, yeah, we get the orange here on the bottom is our polynomial. The blue on the top is our function sign. And so that's what it looks like.